Good day! Nika Jadling, Favorite Casio, on your screens.
Today, we are going to discuss the introduction to Fourier transform.
We're about to transition from Fourier series to Fourier transform.
Let's know further about Fourier transform by defining it.
Fourier transform is a mathematical transformation employed to transform signals between time domain and frequency domain.
It is a tool that breaks a waveform. It's either a function or signal into an alternate representation. It is characterized by sine and cosine.
Did you know that it is named after a French mathematician, Jean-Baptiste Joseph Fourier? He had a crazy idea on 1807. Any periodic function can be rewritten a weighted sum of sines and cosines of different frequencies. Don't you believe it?
Neither did Lagrange, Laplace, Poisson, and other bigwigs.
It is not translated into English until 1878.
But it's true. It is called Fourier transform, possibly the greatest tool used in engineering.
The Fourier transform is a representation of an image as a sum of complex exponential of varying magnitudes, frequency, and phase.
The Fourier transform plays a critical role in broad range of image processing applications, including enhancement, analysis, restoration, and compression.
We have here an example of a Fourier composition of a square wave courtesy of Dr. Dan Russell. Shown on the left part of the image is the time domain signal of the square wave. Can be denoted as a small letter f of t, can be x of t, or also s of t. Any variable can be used as long as it is in terms of time. On the other hand, the frequency domain representation with capital F omega or capital S omega is shown on the right part. F of omega is called the Fourier transform of f of t. In general, f omega or frequency domain is a complex valued function composed of harmonic frequency, phases, and their amplitudes obtained from the Fourier expansion. This next image shows us how Fourier transform works. We have a time domain signal which undergone Fourier transform and frequency domain was given. Fourier transform is a mathematical procedure connecting s of t or the time domain and s of omega or the frequency domain. If time domain or s of t is given, s of omega or the frequency domain may be computed and vice versa.
As we can see, first equation is called the Fourier transform or the forward Fourier transform. The second equation is called the inverse Fourier transform. And as we see, the first equation turns a function of time into a function of frequency. And the second equation, thus the reverse. It turns a function of frequency into a function of time. And this process of turning one into another is called transformation.
Let's define a function f of m that incorporates both cosine and sine coefficients, with a sine series distinguished by making it the imaginary component, which is f of m is equal to f sub m minus I f prime m is equal to integral of f of t multiplied to cosine mt dt minus I multiplied to the integral of f of t multiplied to sine mt dt. Let's now allow f of t to range from negative infinity to positive infinity. So we'll have to integrate from negative infinity to positive infinity. And let's redefine m to be the frequency, which will arrive to f of omega is equals to integration negative infinity to positive infinity of f of t into e to the power of negative I omega t dt. F of omega is called the Fourier transform of f of t. It contains equivalent information to that in f of t. E says that f of t lives in the time domain and f of omega lives in the frequency domain. F of omega is just another way of looking at a function or wave.
The Fourier transform or forward Fourier transform take us from time domain or of f of t to frequency domain or f of omega. Wondering how about the reverse or going back? It's possible to the inverse of Fourier transform. So first, let's recall the formula for the Fourier series of f of t, which is previously discussed by the other group. We have on our screens an equation. F of t is equals to 1 over pi summation from m is equals to 0 to positive infinity f of m cosine mt plus 1 over 2 pi summation from m is equals to 0 to positive infinity f prime m sine mt. Now, let's transform the sums of integrals from negative infinity to positive infinity and again replace the function of m with function of omega. Remembering the fact that we introduced a factor of I or imaginary, we'll have the equation f of t is equals to 1 over 2 pi integral of from negative infinity to positive infinity f of omega e raised to I omega t d omega. So now we have an equation to transform the frequency domain and back.
The Fourier transform does not exist for all non-periodic signals. Hence, for a function x of t to have Fourier transform, the following conditions called Dirichlet's conditions should be satisfied as the function x of t is absolutely integrable over the time interval negative infinity to positive infinity. Integral negative infinity to positive infinity of absolute value of x of t dt less than positive infinity. The function x of t has a finite number of maxima and minima in every finite interval of time. The function x of t has a finite number of discontinuities in every finite interval of time. Also, each of these discontinuities must be finite. Here are some additional information for the introduction of Fourier transform. The Fourier transform was achieved by combining the limit of a periodic Fourier series signal whose period tends to infinity. Classes of signals with a Fourier transform include signals with finite energy and signals meeting the Dirichlet conditions. In most circumstances, a signal's Fourier transform, often known as a spectrum, is a continuous function of frequency with complex values. Both its magnitude and phase often plotted independently. A signal's energy density spectrum plot is the magnitude squared of its spectrum. An integral formula provides the inverse Fourier transform. However, it is frequently possible to conduct a partial fraction expansion of a Fourier transformation, and the time domain signal is frequently derived from a database of Fourier transformation pairs. The Fourier transform of periodic signal can be defined with frequency domain impulses located at the harmonic frequencies, whose areas are a constant times the Fourier series coefficients of signal. In the frequency domain, signal filtering using an LTI system is simply the multiplication of the frequency response of the system with a spectrum of the input signal to either amplify or attenuate different frequencies.
So here are the properties of Fourier transform. We have linearity, time shifting, time or frequency scaling, conjugation and conjugate symmetry, differentiation, integration, convolution, multiplication, energy density spectrum, and Parseval equality. This will be discussed further by the next group, so refer to the next video.